6 times 10 to the minus 47 newtons. So if you have me for chemistry and we talk about this, I always talk about that the electrostatic force in the atom is much, much greater than the force that's associated with the gravitational force in the atom, and now you can see why. I really don't have to worry about that gravitational force or that attractive force in my atoms because the orders of magnitude are so different. That's only 10 to the minus 8, and this is 10 to the minus 47. It's a huge, huge difference. I don't have to worry about that gravitational force between my protons and my neutrons, or my protons and my electrons. So we do have to keep those kind of looking at a variety of different things. So that's kind of fun to kind of look at. So let's just do a couple of problems and how these problems actually get kind of set up. So usually what we're going to do is we're going to get a point charge. I've got a point charge here, and I have a point charge here. And we'll give you a distance between the two. So we're going to use 0.5 meters. And I'm going to warn you today that these numbers I'm using are not from notes. So when we calculate them, they're going to be whatever we're looking at. We're going to say that the charge on this point charge is 8 microcoulombs. And the charge on this point charge, we're going to say, is 5 microcoulombs. We're saying that that's an electron, so it's going to be a negative 5 microcoulombs. If I want to calculate the Coulomb force, it's just K Q1 Q2 divided by R squared. I'm just going to plug in the numbers. Now remember, at this point, it's just the magnitude. Okay, it's just the magnitude. So this is going to be my 9 times 10 to the 9th Newton meters squared coulombs squared. I have 8 microcoulombs, so it's going to be 10 to the minus 6 coulombs. And I have 5 times 10 to the minus 6 coulombs. So this part right here, when you guys plug it into WebAssign and you're working on WebAssign, micro means times 10 to the minus 6. I'll have nano, and that's 10 to the minus 9. You've got to make sure that you convert into coulombs. Otherwise, when you're calculating the newtons, you're going to end up with something funky, and WebAssign is going to give you a wrong answer to start with. So you want to make sure that you've got that straight. And then I've got my 0.5 meters, and that's squared. So my coulombs becomes Coulomb squared, so that cancels. My meters squared are going to cancel. So I'm going to be in newtons, which is exactly what I want. And when I plug that into the calculator, and I'm actually going to show you how I plug it into the calculator, I hope, to see how this goes, because this is one of those times where you've got to figure out on your calculator, zoom in, go down. You've got to figure out on your calculator how to do your exponents, because we're going to be dealing with those exponents a lot. So if I look at my calculator here, this is, you'll have a double E key, or you'll have a 10 to the times something key. So you may have to go dig out your instructions on how to get that. So I've got my calculator on. So I'm going to do my 9 double E and it's to the 9th. So there's that one. Times 8 double E to the minus 6 times, oops, clear. I want to do 5 double E to the minus 6. That gives me my top. Okay? That gives me my top. And if you remember how to do exponents, here's my 9 and my minus 6 times my 10 to the minus 6 times my 10 to the minus 6. That's going to give me minus 12. Okay? That's where that minus 12 comes in. This, and if I add that 9, I end up with something that's a minus 3. And then when I actually do the multiplication, I get my 0.36. So that can kind of help you keep track of, does that number make sense in my calculator? So then I'm going to divide by my 0.5 squared. And I end up with the force between these two charges is going to equal what, or the magnitude of the force is going to be 1.44 newtons. Now you can see why we use microcoulombs, because a coulomb, an actual coulomb of charge is a lot. Okay, an actual coulomb of charge is a lot. Now, when I do this, this now becomes the question of where is this force and where's the vector? Because remember, I have a vector. Vectors have direction and magnitude. So it's going to depend on how WebAssign asks for the problem. So WebAssign may say, what's the force on the -5 microcoulomb charge? So if I want to know what the force on the -5 microcoulomb charge, we know that the magnitude is 1.44. But now I have to kind of look at my picture in order to figure out which direction the force is. These are opposite charges. So on this charge, it's going to want to go this direction. On this charge, it's going to want to go this direction. So the force that I just calculated that answers that question is this force right here. So I have a 1.44 Newton force that's wanting this electron to move to the left. So depending on how we have, and a lot of times on WebAssign, it'll ask you, is it to the left or is it to the right? It'll ask you that question, okay? It'll ask you that question that we have. So that's kind of what we have to start with. Now remember, we also talked about the superposition principle. So now I'm going to do 3 charges. So I'm going to start with a charge here that's a positive charge, and this is going to be my charge 1. I'm going to have a negative charge, and this is going to be my charge 2. I'm going to have a third charge, and this is going to be my charge 3, and I'm going to make it negative. We're going to say that this is 5 microcoulombs. We're going to say that this is 2 microcoulombs, and that's a negative. And we're going to say that this is 6 microcoulombs. Again, I'm just creating numbers. We're going to say that this distance here is 0.4 meters. We're going to say that this distance here is 0.3 meters. Okay? Subscripts are really, really going to help you out in these problems. So what I'm going to do first is I'm not going to worry about what my specific question is. What I'm going to do first is I'm going to calculate the 3 forces. I've got force 1 and 2, so the magnitude of the force between 1 and 2 is going to equal the magnitude of the force between 2 and 1, which is going to equal K Q1 Q2 over R squared. My K is 9 times 10 to the 9th, Newton meters squared, coulombs squared. My charge is 5 times 10 to the minus 6 coulombs, and 2 times 10 to the minus 6 coulombs, and I'm 0.4 meters squared. So I'm going to plug that into the calculator and see what I get. If I plugged it in the calculator correctly, I got 5.6 or 5.5625 newtons. So this is the force between charges 1 and 2. So now I'm going to do the force between charges 1 and 3. Subscripts are going to help me out, so it keeps track of which forces I'm playing with. So this time it's going to be Q, Q1, Q3 divided by R squared. So I get my 9 times 10 to the 9th. And on my picture, I've got my 5 times 10 to the minus 6 coulombs. And I have my minus 6 times 10 to the minus 6. Except I don't have to worry about that because I'm just doing magnitude, coulombs. But now my distance between 1 and 3 is 0.7. So this is going to be 0.7 meters, and that's squared. So I plug that into the calculator and see what I get. This gives me 0.551 newtons. So I've got 2 of the 3. I now have to do the last one, force 2, 3, which is equal to force, the magnitude of force 3, 2, which is going to be my K, Q, 2, Q, 3, divided by the distance between those two squared. So if I do that one, I get 9 times 10 to the 9th. Q2 was 2 times 10 to the minus 6 coulombs. Q3 was 6 times 10 to the minus 6 coulombs. And the distance between those two was 0.3 meters squared. So now I plug that into the calculator. This gives me 1.2 newtons. So I have the values all the way through, so I'm going to rewrite them down here so we can see. So F13, the magnitude of that one was 0.5625 newtons. Magnitude of, this is F12. Magnitude of F13 was 0.551 newtons. And the magnitude of F23 was equal to 1.2 newtons. So I have all 3 magnitudes. Now comes the fun part. We're going to use the superposition principle, and we're going to know what question we ask. So if WebAssign asks me what's the force on charge 2, WebAssign is going to ask me what's the force on charge 2. What's the force that charge 2 is experiencing? Well, if I look at this, and I look at this conceptually, we know that this force here, this is going to be the force 1 and 2, because it's going to want to be attracted to this one. So this one is going to be force 1, 2 on the charge in the middle. If I'm looking at how these two interact with each other, this force is force 1, 3. So that's going to be attractive because I'm going to disregard this middle one, and I'm just looking at how this one is impacting that one right there. If I look at this charge, force 1, 3 goes that way, but force 2, 3 goes that way. Because these are both like charges, and like charges repel. So if I look at this one, this is force 2, 3, because it's being repelled by that one. So now if I want to calculate the force here, I'm going to look at the force 1, 2 plus the force 2, 3. But this time they're both going to be adding vectors that look like this. So I'm going to put in here a negative 0.5625 and a negative 1.2 to give me the actual resultant force. So this gives me a 1.7625 Newton with a negative, and it's going to be moving to the left. So I'm using the superposition principle to help me look at the forces. So when I'm working these electrostatic force problems, it's a lot easier to start and calculate the magnitudes, then look at my picture to look at how they're going to add up. So let's look at what the force is on charge 3. So this is the force on charge 2. So let's look at the force on charge 3. In this case, I'm going to have force 2, 3, which goes this direction, minus force 1, 3, which goes that direction. So I'm going to put these numbers in. I'm going to get 1.2 newtons minus 0.5625 newtons. And when I do that one, I get 0.6375. So this one is going to want to go that direction. So this is the force resultant on 3. The force resultant on 2 went that direction. And we know that the force resultant for the force 1 is going to go this direction because they're both of those are negative. So that's all well and good when it's in one dimension. Your homework problems and everything else are going to be in 2 dimensions. A lot of two-dimensional problems. So let's look at a two-dimensional problem. So I'm going to give myself a grid. I'm going to put a charge here on the grid. We're going to call this a positive 6 microcoulomb charge. Up here, we're going to get a negative 3 microcoulomb charge. And over here, I'm going to get a negative 5 microcoulomb charge. We're going to say that this distance here is 0.5 meters, and we're going to use this distance here as 0.3 meters. Well, kind of need to know a couple other things. We want to know the force on this charge. So we want to know that force because we want to know how this charge is going to move with respect to those other ones. Because if I look at this right now as it stands and conceptually look at how this is going, we know that I've got a force here that's being added, and we know that I've got a force that's going up that direction that's being added. So if I look at my force diagram, I've got this right here, remembering that I could do this, and my resultant force is going to be something like this. So this one we know is going to go off in some direction just like that. The question is, what's this angle? Because these aren't the same magnitude. I have 2 different types of charges. So I've got a challenge here. I've got a challenge that I gotta work out. Okay, I got a challenge that I gotta work out. So I also need another piece of information that I need here is I might need this distance. I might need that distance, that R, but I can get that distance, right? If I have a right triangle, this is 0.5, this is 0.3, C squared is equal to 0.3 squared plus 0.5 squared. If I do that, 0.3 squared plus 0.5 squared. This gives me 0.34. C is going to equal the square root of that. It's going to be 0.58. So I have that R if I need it. So the first thing I got to do is calculate the magnitude. So the magnitude between the 6 and the 5 is going to equal 9 times 10 to the 9th. The charge, 6 times 10 to the minus 6 times 5 times 10 to the minus 5, or 6, divided by my 0.5 meters squared. Put that into the calculator. get 1.08 newtons. The force between 6 and 3 gives me 9 times 10 to the 9th. And I get my 3 times 10 to the minus 6. And I get my 6 times 10 to the minus 6. And then I'm going to divide by my 0.3 meters squared. Put that one in. This gives me 1.8 newtons. All right. Because of how I set, you got a question?
On the 3 times 10 to the negative 6, would that not be negative 3?
I'm doing magnitude, so I don't have to worry about, I'm doing magnitude, so I don't have to worry about positives and negatives just yet. Okay? I'm doing magnitude. So now let's look at this. So here's my picture. The force between 5 and 6, so if I write this out as my vector component between 5 and 6, so I'm using 5, 6 to keep track of what this is. We know that if I'm looking at it from this perspective, sitting at this charge, looking at it from this perspective, the force is going to equal 1.08 newtons only in the I direction, okay? Because it's only going that direction due to that negative charge. Now my vector for the other one, my vector for the 6, 3, it's an attractive force. It's only in the Y direction, so I get 1.8 newtons in the J direction. Again, it's an attractive force, so both of these are going to be positive. My resultant force, remembering how we did it back last semester, I'm going to add these two vectors, and because these are in different components, I end up with 1.08 in the I direction plus 1.8 in the J direction. So now I actually have the vector representation of that vector. So now I can calculate the magnitude of that vector. That's just going to be the square root of 1.08 squared plus 1.8 squared. And when I do that, this gives me, it looks like something on the order of 2.1 newtons. So the magnitude is 2.1 newtons. My angle, remember my angle is going to be the arc tangent of my y, 1.8 divided by my 1.08 is going to give me my angle. And that's going to be 59 degrees. So this vector actually is going to go, looks something like this, where this magnitude is 2.1 newtons, and my angle ends up being 59 degrees. Now, the question is, does that make sense? Does that really make sense? And the answer is it kind of does, because what happens is, remember the force drops off as 1 over r squared. So even though that this is a bigger charge, it's much further away. So this one is actually going to pull it more towards that direction, just because I end up with the distances between the charges. So I get a lot of different pieces that are going on. So let's do another one of those, just so that you can kind of see how this might work as we change up the dimensions. So I'm going to do this one. I'm going to do one that looks like this. All right. So I'm going to put a charge here. This time I'm going to put a -3 microcoulomb charge. And we're going to say this distance is 0.2 meters. We're going to put another charge here, and I'm going to make this one a +4 microcoulomb charge. And we're going to say that this distance is 0.4 meters. I'm going to put a third charge up here, and I'm going to make this one a 6 microcoulomb charge. And this one is going to be a distance of 0.5 meters. This time we want to find the force on this charge due to this configuration. So now I've got to do some quick arithmetic here. I got to figure out that side. So this side is c squared is equal to a squared plus b squared. That's going to be my 0.2 squared plus my 0.5 squared. Which if I do that, 2 squared plus 0.5 squared gives me 0.29. So c is going to be the square root of that. So c is 0.54 meters. So this side is 0.54 meters. This side is going to be 0.5 squared plus 0.4 squared gives me 0.65. C equals the square root of that. 0.81 meters. So the easy part, of course, is going to be doing the calculation. So my force between my 6 and my 4 is just going to be my 9 times 10 to the 9th. And I'm going to get my 6 times 10 to the minus 6. And I'm going to get my 4 times 10 to the minus 4. And I'm going to divide that by my 0.81 squared. Then I've got my force over here between the 3 and the 6. I get my 9 times 10 to the 9th. I get my 6 times 10 to the minus 6. I get my 3 times, that should be minus 6, my 10 to the minus 6, divided by my 0.54. But let's look what happens here. So if I have, and I'm going to look at it from this perspective. So here's my charge. In this case, this force wants to go here. So that's the force due to 3, 6. That's negative, that's positive. These two are both positive. So now I get the force for 6, 4. I get that force. So I've got to do a couple of things in order for me to be able to solve this problem. I got to figure out some angles. Okay? I got to figure out some angles because I need to be able to write force 6, 4 in terms of its I and J coordinates. I've got to be able to write force 6, 3 in terms of its I and J coordinates. So I got to figure that out. So we can do a couple of different things. I can look at this angle here. And if I do, this is going to be, if I do cosine, so I can do cosine of the angle is equal to the adjacent over the hypotenuse. So my angle is going to be the arc cosine. My adjacent is 0.5. my hypotenuse, we figured it out as 0.54. That's gonna give me, when I do that angle, gives me an angle of 22.2 degrees. So that's that angle. So if I'm writing out this force, this one is going to be negative, and this will also be negative because I've got my components here. So there's my x component, and this is my y component. So both of them are going in the negative direction. So if I do this, I'm going to write whatever this magnitude is, so the magnitude of 3,6, whatever that value is, magnitude of 3,6 minus cosine of 22, nope, it's going to be opposite. It's going to be sine 22.2 degrees in the I direction minus f36 cosine of 22.2 degrees in the j direction. Just to kind of remind you so that you guys aren't too terribly confused, although you probably are. Here's my vector. This is vector 3,6. This is vector 3,6 in the y direction. That's the angle that I have. That's why I'm going to get a negative f36 cosine of the angle in the j direction. Because this is the angle that I know, this becomes the adjacent side. That's why I'm going to do the cosine. This one here, f36 in the x direction, is going to be negative f36 sine of 22.2 degrees in the I direction, because this is the opposite side from the angle that I know. And it's all about the angle that I know. And so whatever I calculated this value to be, and let's go ahead and plug in the value and calculate it. I didn't stop and do that, so we'll do it now. Remember, I gotta square that. That number does not look right. That looks better. This number worked out to be 0.556. Doing this one, because I'll need it in just a second. This one gives me 0.329. These are all in newtons. So now if I do that, this becomes times cosine 22.2. This becomes a negative 3.305. This becomes, oops, no, sorry. This is 0.556 times my cosine of 22.2 degrees. That's a negative 556 cosine 22.2. This becomes minus 514, 0.514, 0.556 cosine, 22.2. This one becomes a minus 0.21. So my vector F36 looks like minus 0.514. I'll write it out. Minus 0.21 newtons in the I direction, minus 0.514 in the J direction. I can do the same thing for this vector. So let's look at that vector. So this time I've got, this is being repulsive here. I can find this angle doing the same thing that I did there. So if I do that, this side was 0.5, this side is 0.4. So my angle is the arc tangent of my opposite side, 0.4 divided by my 0.5. This gives me, this angle is 38.65 degrees. Now this angle and this angle are going to be the same. I can use my trigonometric identities to get that. So those two angles are the same. So now my force 6.4, it's going to be in the positive y direction and the negative x direction. So I'm going to get, so this will be 6.4x, and this is going to be, and that's in the I, and this is positive 6.4y in the j. And when I do that, F64x is going to equal, so there's my x part, minus 0.329 sine of 38.65 degrees. Do that. 0.329 times sine 38.65. This is 0.205 in the negative, and F64 in the y is my 0.329 cosine of 38.65. This gives me 0.257. And so this vector looks like this. Minus 0.205i plus 0.257j. So if I have those two things, need a piece of paper. So I have two vectors. I have vector 6.4 and vector 3.6. This gives me my minus 0.205 in the I plus 0.257 in the J. This one was minus 0.21 in the I, minus 0.514 in the J. The resultant vector is going to be minus 0.205 minus 0.21 in the I plus 0.257 minus 0.51 in the J. And then I can do exactly what I did before, calculate the magnitude, and I can calculate the angle, and then we would know what direction this particular charge is going on with. And that's all I got time for. Test on Friday on sound.
You get the cheat sheet?
You get to build your cheat sheet.
Yes.
written on it.